there is a planet in our solar system that could swallow every other world whole and still have room to spare. A planet so massive that it warps the fate of everything around it. A planet that, according to our best physics, should not look the way it does, should not behave the way it does, and should not be where it is. That planet is Jupiter, and almost everything you were taught about it is either incomplete or wrong. Consider this. Jupiter contains more mass than all the other planets in the solar system combined. Not just a little more, 2.5 times more. Its diameter stretches roughly 143,000 kilometers, which means you could line up more than 11 Earths across its face. Its volume could contain over 1,300 Earths. The Great Red Spot alone, a storm that has been raging for at least 350 years, could fit 2 or 3 Earths inside it. These are not metaphors. These are measurements. This is geometry. But here is what most people never hear. Jupiter is not simply a big ball of gas passively floating in space. It is an active, violent, deeply strange object that has shaped the architecture of our entire solar system. It flung worlds into the void. It redirected asteroids and comets. It may have delayed or accelerated the development of life on Earth. Some scientists believe that without Jupiter, complex life might never have arisen at all. Others believe Jupiter nearly destroyed the inner solar system before Earth even had a chance to form. The story of Jupiter is not just the story of a large planet. It is the story of why we exist. It is the story of how chaos produced order, and how that order hangs on conditions we barely understand. And consider this. Jupiter rotates faster than any other planet in the solar system. One full rotation takes just under 10 hours. 10 hours. A day on Jupiter is less than half a day on Earth. This furious spin rate, combined with Jupiter's gaseous composition, means the planet is not a perfect sphere. It is visibly flattened, bulging at the equator and compressed at the poles. The equatorial diameter is roughly 9,300 kilometers wider than the polar diameter. You can see this oblateness, this squashed shape, through a good amateur telescope. The planet is spinning so fast that it is being pulled apart at the waist, the equatorial material flung outward by centrifugal force, resisting the inward pull of gravity. It is a planet at war with itself, gravity pulling in, rotation pushing out, and the result is a shape that betrays the violence hidden beneath those serene-looking cloud bands. And it gets stranger still. Deep inside Jupiter, the pressures are so extreme that hydrogen, the lightest and simplest element in the universe, is crushed into a liquid metal, not a gas, not a solid, a metallic liquid that conducts electricity and generates a magnetic field 20,000 times stronger than Earth's. This magnetic field stretches so far into space that if you could see it with your eyes, Jupiter's magnetosphere would appear larger than the full moon in our night sky. The radiation environment near Jupiter is so intense that it would kill an unprotected human in minutes. Spacecraft that visit Jupiter must be armored in titanium vaults to protect their electronics from radiation levels that rival a nuclear reactor. This is not a gentle giant. This is a monster hiding in plain sight. Jupiter broadcasts its violence across the electromagnetic spectrum. Its aurorae, shimmering ovals of ultraviolet and X-ray light crowning both poles, are hundreds of times more energetic than the northern lights on Earth. They are not driven primarily by the solar wind, as Earth's aurorae are, but by the volcanic emissions of its moon Io, whose sulfur and oxygen ions spiral along magnetic field lines and crash into Jupiter's upper atmosphere at enormous speeds. Jupiter also emits powerful bursts of radio waves, decametric emissions, that were first detected from Earth in 1955 by Bernard Burke and Kenneth Franklin, who initially thought they had found a faulty antenna. What they had found instead was a planet shouting into the void, announcing its magnetic fury in wavelengths that carry across hundreds of millions of kilometers of space. Jupiter was the first planet discovered to be a radio source. It was a hint, decades before the first spacecraft arrived, that this world was far more active and far more dangerous than anyone imagined. By the end of tonight, you're going to understand why Jupiter challenges nearly every assumption we have about planets, about our solar system, and about how worlds form. You are going to learn what the Juno spacecraft discovered when it peeled back the cloud tops and looked inside, a discovery that left planetary scientists scrambling to rewrite their textbooks. You are going to confront the possibility that Jupiter once migrated through the solar system like a wrecking ball, reshaping the orbits of every planet it passed. And you are going to sit with the unsettling idea that this one object, spinning silently in the dark 5 times farther from the Sun than our own world, holds the key to questions we have barely begun to ask. Questions about whether our existence was inevitable, or whether it was a cosmic accident that required precisely the right kind of monster at precisely the right distance. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what Jupiter truly is, we first need to understand what it is not. Jupiter is not a failed star, despite what many popular accounts suggest. It is not simply a bigger version of Earth, and it is not the placid, striped marble that appears in textbook photographs. Jupiter is something far more complex, something that sits in a category almost entirely its own, a category that planetary scientists are still trying to define after centuries of study. Let us start with size, because size is where our intuitions first break down. Jupiter orbits the Sun at an average distance of about 778 million kilometers. That is roughly 5.2 times the distance between Earth and the Sun, a unit of measurement called an astronomical unit. Light from the Sun takes about 43 minutes to reach Jupiter. Light travels at nearly 300,000 kilometers per second, the fastest speed possible in the universe, and even at that unimaginable velocity, it takes the better part of an hour to cross the gulf between us and Jupiter. If you could somehow drive a car at highway speed, roughly 100 kilometers per hour, without ever stopping for fuel or rest, it would take you over 880 years to reach Jupiter from Earth at its closest approach. 880 years. That is longer than the entire span from the signing of the Magna Carta to the present day. Longer than the entire age of most European nations. And Jupiter is not even close to the edge of our solar system. It sits in the middle zone, a kind of boundary marker between the rocky inner worlds and the frozen outer giants. Beyond Jupiter lie Saturn, Uranus and Neptune, worlds even more remote and even more mysterious. The outer solar system is vast beyond comprehension, and Jupiter guards its entrance. Now consider mass. Jupiter weighs approximately 1.9 times 10 to the 27th kilograms. Written out in full, that is a number so large it loses all meaning, so let us translate it. If you placed every other planet in the solar system on one side of a cosmic scale, Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury and Jupiter on the other side, Jupiter would outweigh them all, combined, by a factor of 2.5. Earth's mass is roughly 6 times 10 to the 24th kilograms. Jupiter is about 318 times more massive. Imagine 318 Earths compressed and merged into one body. Not 318 Earths side by side, but crushed together, fused. All that rock and water and iron squeezed into one immense sphere of gas and liquid metal. That is Jupiter. That is the scale of what we are dealing with. Here is a comparison that might help. If the Sun were the size of a typical front door, about 2 meters tall, then Jupiter would be roughly the size of a basketball. Earth would be the size of a pea, a small green pea. You could hold Earth between your thumb and forefinger and lose it in a pocket. Jupiter would fill your cupped hands, and the Sun would tower above you, filling an entire doorway, radiating heat you could feel from across the room. This is the hierarchy of our cosmic neighborhood. We are small, Jupiter is formidable, and the Sun dwarfs everything. Here is another way to feel the scale. If you could somehow shrink the entire solar system so that the Sun were the size of a grain of sand, roughly 1 millimeter across, then Jupiter would be a barely visible speck about 5 meters away. Earth would be microscopic, invisible to the naked eye, about 1 meter from the sand-grained Sun. And the nearest star, Proxima Centauri, would be another grain of sand, roughly 29 kilometers away. 29 kilometers. On a scale where the Sun is a grain of sand, the nearest star is a half-hour drive. We are profoundly isolated. And within that isolation, Jupiter is the dominant gravitational force after the Sun itself. But mass alone does not make Jupiter strange. What makes Jupiter strange is what that mass is made of and how it behaves under the conditions that exist inside the planet. Jupiter is composed almost entirely of hydrogen and helium, the two lightest elements in the periodic table, roughly 75% hydrogen and 24% helium by mass, with the remaining 1% consisting of trace amounts of heavier elements, methane, ammonia, water, and various other compounds. In its outermost layers, the atmosphere is a swirling mixture of hydrogen gas, helium, ammonia crystals, ammonium hydrosulfide clouds, and water vapor. These clouds form the famous bands and zones visible through even a modest backyard telescope, alternating stripes of light and dark that wrap around the entire planet like the rings of a barrel. The light bands, called zones, are regions of rising gas, cooler and higher in the atmosphere. They appear bright because the ammonia ice crystals at their tops reflect sunlight efficiently. The dark bands, called belts, are regions of sinking gas, warmer and lower. They appear darker because we are seeing deeper into the atmosphere, where the clouds are thicker and composed of different materials. Between these bands, winds howl at speeds that exceed 500 kilometers per hour. Some jet streams on Jupiter blow at over 600 kilometers per hour, faster than the speed of sound in Earth's atmosphere. The jet streams on Jupiter make Earth's fiercest hurricanes look like a gentle breeze on a summer afternoon. But the atmosphere, spectacular as it is just the skin. A thin, beautiful, violent skin stretched over something far stranger. Go deeper, and the physics transforms in ways that challenge our everyday understanding of matter. The visible atmosphere that we photograph and study, the swirling bands and spinning storms that define Jupiter in the popular imagination, represents less than 1% of the planet's radius. Everything that makes Jupiter truly extraordinary lies beneath, hidden from view, accessible only through indirect measurements, gravity science, magnetic field mapping, and the careful interpretation of data transmitted by robotic emissaries across 500 million kilometers of empty space. At a depth of roughly 1,000 kilometers below the visible cloud tops, the pressure increases to about 10 times the atmospheric pressure at sea level on Earth. The temperature rises to perhaps 2,000 degrees Celsius. The hydrogen is still a gas here, but it is thickening, becoming denser with every kilometer of descent. There is no boundary, no wall, no transition you could point to and say, here the atmosphere ends and the interior begins. The gas simply becomes denser and denser, hotter and hotter, compressed by the weight of everything above it. By the time you descend to around 5,000 kilometers, the pressure has risen so much that hydrogen transitions from a gas into a liquid. Again, there is no surface, no ocean with a shore, no boundary you could stand on or float upon. The gas becomes a fluid in a continuous gradient, like steam thickening into fog, thickening into mist, thickening into rain. Jupiter has no solid ground. There is no ground. If you fell into Jupiter, you would never land. You would descend through thickening gas, then through hot liquid hydrogen, pressed by increasing weight, heated by increasing temperature, until you were simply absorbed, dissolved into the planet itself, like a grain of salt dropped into warm water. Your spacecraft, no matter how robust, would eventually be crushed. The Galileo probe, the only object we have ever sent into Jupiter's atmosphere, survived for about 57 minutes before the pressure and heat overwhelmed it at a depth of roughly 150 kilometers. It barely scratched the surface. If Jupiter has a surface at all, it lies tens of thousands of kilometers deeper, in conditions no human technology can withstand. This absence of a solid surface is one of the features that makes Jupiter conceptually alien. We are creatures of surfaces. We walk on ground. We build on foundations. We think in terms of boundaries, inside versus outside, up versus down, land versus sky. Jupiter offers none of these distinctions. Its entire structure is a continuous gradient, a seamless progression from thin gas to thick gas, to compressed fluid, to liquid metal, to whatever remains at the center. There are no walls, no floors, no edges, only density increasing with depth, temperature rising with pressure, and matter transforming gradually from one state to another in a single, unbroken continuum. If you could somehow survive the descent, you would never know when you had passed from atmosphere to interior. The transition is invisible, defined only by the mathematics of pressure and temperature, not by any physical boundary you could touch or see. Go deeper still. At a depth of perhaps 15,000, to 20,000 kilometers below the cloud tops, something extraordinary occurs. The pressure reaches roughly 2 million times the atmospheric pressure at Earth's surface. At this crushing depth, hydrogen undergoes a phase transition that defies everyday experience. The hydrogen molecules are squeezed so tightly together that the electrons, normally bound to individual protons, break free. They become delocalized, shared among all the atoms, forming a sea of protons swimming in a communal electron cloud. This substance is called metallic hydrogen. It is a liquid metal made from the lightest element in the universe. It conducts electricity like copper or aluminum. It flows and churns with the planet's rotation, and those flowing electrical currents generate Jupiter's staggering magnetic field. Jupiter's magnetic field is the largest and most powerful of any planet in the solar system. It is roughly 20,000 times stronger than Earth's at the cloud tops, and its influence extends far out into space, creating a magnetosphere, a region of space dominated by the planet's magnetic field that dwarfs the planet itself. Jupiter's magnetosphere extends roughly 5 million kilometers sunward, about 35 times the diameter of the planet. In the opposite direction, away from the Sun, the magnetotail, the elongated downstream wake of the magnetosphere, stretches for over 700 million kilometers, reaching past the orbit of Saturn. If you could see Jupiter's magnetosphere glowing in the night sky from Earth, it would appear several times wider than the full moon. It is the largest coherent structure in the solar system, other than the heliosphere itself, the Sun's own magnetic domain. Within this magnetosphere, Jupiter traps and accelerates charged particles, protons and electrons from the solar wind, and sulfur and oxygen ions blasted into space by Io's volcanoes, creating radiation belts of staggering intensity. The most energetic particles in Jupiter's radiation environment carry energies of tens of millions of electron volts, sufficient to penetrate centimeters of aluminum shielding and destroy unprotected electronics. The radiation dose near Jupiter's equator at the orbit of Io is so intense that an unshielded human would receive a lethal dose in minutes. This radiation environment has been the single greatest engineering challenge for every spacecraft ever sent to Jupiter, and it is a direct consequence of the metallic hydrogen interior which generates the field and the volcanic moon Io, which supplies the charged particles that the field traps and accelerates. No laboratory on Earth has ever sustained metallic hydrogen in a stable, lasting state. Scientists have glimpsed it in brief, fleeting experiments using diamond anvil cells, devices that crush tiny samples between the polished tips of 2 gem-quality diamonds at pressures exceeding 300 gigapascals. In 2017, a team at Harvard University led by Isaac Silveira and Ranga Dias reported producing metallic hydrogen at a pressure of roughly 495 gigapascals, though the result was controversial and the sample was lost when one of the diamonds shattered. Jupiter produces these conditions naturally, effortlessly, across a volume larger than most planets. The metallic hydrogen layer inside Jupiter may extend from around 15,000 kilometers below the cloud tops all the way down to a depth of roughly 55,000 kilometers or more. That is a shell of liquid metal thicker than the diameter of Neptune, the 4th largest planet in our solar system. And then there is the core. For decades, scientists assumed Jupiter had a compact, dense core of rock, metal, and ice at its center, perhaps 10 to 20 times the mass of Earth. This core was thought to be the seed around which the planet originally formed. The nucleus that gravitationally attracted the hydrogen and helium envelope. The standard model of giant planet formation, called core accretion, proposed that this rocky core grew large enough, roughly 10 Earth masses, to trigger runaway gas capture from the surrounding solar nebula. Once that threshold was crossed, gas poured onto the growing planet at an accelerating rate, and Jupiter ballooned into the behemoth we see today. The core was the foundation. The gas was the building material. The theory was clean, intuitive, and widely accepted. But the Juno spacecraft, which entered Jupiter's orbit on the 4th of July 2016, upended this picture. Juno's gravity measurements, the most precise ever obtained for any giant planet, revealed that Jupiter's core is not a neat, compact ball. It is diffuse, spread out, diluted, The heavy elements that should have been concentrated at the center appear to be mixed into the surrounding hydrogen and helium, extending outward to perhaps 30 to 50% of the planet's radius. Scientists call this a fuzzy core or a dilute core. It was one of the most surprising results in planetary science in recent memory, a finding that appeared in the journal Nature in 2019 and prompted a wave of new theoretical work. Something happened to Jupiter's core. Something broke it apart or prevented it from ever fully consolidating. And that question, the question of what happened inside Jupiter, connects to a much larger, much more unsettling mystery. A mystery about how Jupiter formed, where it formed, and what it did to the rest of the solar system as it grew. To appreciate the stakes of this mystery, consider one more scaled comparison. Imagine the solar system compressed so that the distance from the Sun to Earth is just 1 meter. A single step. On this scale, Jupiter would be about 5.2 meters away, across a small room. Saturn would be nearly 10 meters away. Neptune, the outermost major planet, would be 30 meters away, at the far end of a basketball court. The Kuiper Belt, the ring of icy bodies beyond Neptune, would extend to perhaps 50 meters, and the nearest star, Proxima Centauri, would be over 270,000 meters away, 270 kilometers. On a scale where Earth is one step from the Sun, the nearest star is a 3-hour highway drive. We are profoundly, staggeringly alone, and within that solitude, Jupiter is the dominant presence, the most massive object after the Sun, the gravitational anchor of the outer solar system. Jupiter's gravity has been shaping the solar system for 4.5 billion years. It influences the orbits of asteroids. It perturbs comets, redirecting them toward the inner solar system or flinging them out into interstellar space. It creates resonances, gravitational patterns that lock smaller bodies into specific orbital relationships, like a metronome synchronizing a room full of clocks. The Kirkwood gaps in the asteroid belt, regions where almost no asteroids exist, are carved by orbital resonances with Jupiter. Asteroids in those gaps would be subjected to repeated gravitational tugs at predictable intervals, pumping up their orbital eccentricities until they were ejected or sent crashing into the Sun or a planet. Jupiter does not merely influence the asteroid belt, it sculpts it, it maintains it, it defines its boundaries and its structure. To feel this in human terms, imagine you are standing in a stadium, a large football stadium with a capacity of 80,000 people. Now, imagine the stadium is completely empty except for a single grain of sand sitting at the center of the field. That grain of sand represents the total mass of the asteroid belt, roughly 4% of the Moon's mass, spread across a region of space hundreds of millions of kilometers wide. Jupiter keeps that grain of sand in place. Jupiter carved the gaps in the dust. Jupiter determines which orbits are stable and which are death sentences. An object the size of a small planet, orbiting hundreds of millions of kilometers away, controls the fate of pebbles and boulders scattered across a vast ring of space. That is gravitational authority. That is Jupiter. Now consider an even more telling comparison. If you compressed all of human history, everything from the first cave paintings to the present moment, into a single day, 24 hours from midnight to midnight, then the earliest written records would appear at roughly 11:45 in the evening. The entire age of modern science, from Galileo to now, would fit into the last 3 minutes. And Jupiter has been reshaping the solar system for the equivalent of roughly 365,000 such days. It has been at this work since before the Earth had a solid surface, since before the Moon existed, since the solar system itself was a swirling cloud of debris, planetesimals, and young planets careening through the dark. Everything we see today, every orbit, every gap, every resonance, bears the imprint of that long, patient, gravitational influence. The Trojan asteroids, two vast clouds of rocky and icy bodies, orbit the Sun at the same distance as Jupiter, locked into gravitationally stable points called Lagrange points, 60 degrees ahead of and behind the planet in its orbit. Jupiter has gathered roughly 12,000 known Trojans at last count, and the true number may be far higher. Some of these objects are over 100 kilometers across. They are not debris. They are captured worlds, prisoners of Jupiter's gravity, forced to march in lockstep with the giant planet around the Sun. Galileo Galilei first observed Jupiter through a telescope in January of 1610. He saw 4 bright points of light near the planet, points that shifted position from night to night. These were the 4 largest moons of Jupiter, now called the Galilean moons: Io, Europa, Ganymede, and Callisto. Galileo's observation was revolutionary, not merely for what it revealed about Jupiter, but for what it implied about the cosmos. It proved that not everything in the sky orbits Earth. Other worlds had their own companions. The Earth was not the center. Galileo's discovery provided direct observational evidence for the heliocentric model proposed by Copernicus, the idea that Earth and the other planets orbit the Sun. Jupiter did not just change our understanding of the solar system. It changed our understanding of our place in existence. Today, we know Jupiter has at least 95 confirmed moons, with new ones still being discovered. Its moon system is like a miniature solar system, a collection of worlds with their own geology, chemistry, and in at least one case, their own ocean. Europa, the smallest of the 4 Galilean moons, is believed to harbour a liquid water ocean beneath its icy crust, an ocean that may contain 2 to 3 times more liquid water than all of Earth's oceans combined. Ganymede, the largest moon in the entire solar system, is bigger than the planet Mercury. It has its own internally generated magnetic field, the only moon known to possess one. Io, the innermost Galilean moon, is the most volcanically active body ever observed. Its surface, a hellscape of sulfur flows and erupting vents, constantly reshaped by tidal heating, driven by the gravitational tug-of-war between Jupiter and the outer moons. These are not footnotes, these are worlds. Worlds with mountains and valleys, with oceans and volcanoes, with the potential, in the case of Europa, to harbour life. And they all exist because of Jupiter. They orbit Jupiter because its gravity captured and held them. They are heated and tortured because Jupiter's immense mass stretches and squeezes them as they orbit. They are shielded from some threats and exposed to others because Jupiter's magnetic field bathes them in radiation. The Jovian system is a study in gravitational power, in the way a single massive body can create, sustain, and destroy entire worlds. Yet, for all we have learned over 4 centuries of observation, the deepest truths about Jupiter have only begun to emerge in the last decade. The Juno mission, designed specifically to peer beneath the cloud tops and probe the interior structure, has revealed a planet that is far more turbulent, far more complex, and far more mysterious than anyone expected. The data from Juno has forced scientists to reconsider not just how Jupiter formed, but how giant planets form anywhere in the universe. And this matters because Jupiter-like planets, the gas giants, are among the most common types of worlds we detect around other stars. Understanding Jupiter is not just about understanding one planet. It is about understanding the architecture of planetary systems throughout the galaxy, across the full breadth of the Milky Way. But here is the problem. The more we learn about Jupiter, the less it fits into our existing models. Something is wrong with our assumptions. And the story of what went wrong begins not in the clouds of Jupiter, but in the swirling disk of gas and dust where our solar system was born 4.5 billion years ago in an unremarkable corner of an unremarkable galaxy. 4.5 billion years ago, our solar system did not exist. In its place, there was a vast cloud of gas and dust, a molecular cloud drifting through the Milky Way, cold and dark and utterly unremarkable. Thousands of such clouds exist in our galaxy today, visible in photographs as dark patches against the glowing backdrop of more distant stars. They are made of hydrogen and helium, with traces of heavier elements forged in the cores of stars that lived and died before our sun was born. Carbon, oxygen, silicon, iron, all cooked in the nuclear furnaces of earlier stellar generations and scattered into the interstellar medium by supernova explosions. We are, as the astronomer Carl Sagan famously noted, made of star stuff, and so is Jupiter, and so is everything. Then something disturbed the cloud. Perhaps a nearby supernova sent a shockwave rippling through the gas, compressing it beyond a critical density. Perhaps the gravitational tide of the galaxy's spiral arms nudged a region of the cloud past the tipping point. Perhaps it was simply the natural turbulence of the interstellar medium, random motions creating pockets of density that grew and amplified under their own gravity. Whatever the trigger, a portion of this cloud began to collapse. As it collapsed, it spun faster, obeying the law of conservation of angular momentum, the same principle that makes an ice skater spin faster when she pulls her arms in close to her body. The spinning cloud flattened into a disk, a vast rotating platter of gas and dust with a growing concentration of mass at its center. At that center, temperatures and pressures rose higher and higher as material poured inward, until finally, roughly 4.6 billion years ago, the temperature exceeded 10 million degrees Celsius and nuclear fusion ignited. Hydrogen atoms began fusing into helium, releasing energy. A star was born on our star, the Sun. The disk that remained around the young Sun, the solar nebula, was the raw material from which every planet, moon, asteroid, and comet in our solar system would eventually form. This disk was not uniform. Close to the Sun, where temperatures were high, sometimes exceeding 2000 degrees Celsius, only the most heat-resistant materials could exist as solids. Metals like iron and nickel, and rocky minerals called silicates. Volatile materials like water, methane, and ammonia were vaporized by the Sun's heat and remained as gas. This meant that close to the Sun, the solid particles available to build planets were exclusively rock and metal. These particles collided, stuck together through electrostatic forces and gentle collisions, and gradually built up into larger bodies called planetesimals, objects ranging from a few hundred meters to several kilometers across. The planetesimals continued colliding and merging, a process called accretion, and over millions of years, they grew into the rocky protoplanets that would become Mercury, Venus, Earth, and Mars. But farther from the Sun, beyond a boundary called the snow line, located at roughly 2.5 to 4 astronomical units from the Sun, depending on the model and the epoch, temperatures dropped below the freezing points of water, ammonia, and methane. Beyond this line, these volatile materials could condense into solid ice, adding enormously to the inventory of solid material available for planet building. The snow line was a multiplier. Inside it, only rock and metal were solid. Outside it, rock, metal, and ice were all solid. The total mass of solid material beyond the snow line was perhaps 3 to 4 times greater than inside it. The planetesimals that formed beyond the snow line were larger, they grew faster, they accumulated mass more quickly. And this is where Jupiter enters the story. The standard model of giant planet formation, called core accretion, proposes a specific sequence of events. First, a rocky and icy core forms beyond the snow line, growing by the same process of accretion that builds the terrestrial planets, but faster, because there is more solid material available. This core grows steadily for perhaps 1 to 3 million years, sweeping up planetesimals from the surrounding disk. When the core reaches a critical threshold, roughly 10 Earth masses, its gravity becomes strong enough to attract and hold not just solid particles, but the hydrogen and helium gas that makes up the vast majority of the solar nebula. Gas begins to fall onto the core, slowly at first, accumulating in a thick envelope. But as the gas envelope grows, its gravitational pull increases, attracting even more gas. A feedback loop takes hold, the accretion rate accelerates. Within a relatively short time, perhaps a few 100,000 years, the planet undergoes what is called runaway gas accretion, doubling and tripling its mass in rapid succession until it has swept up a huge fraction of the available gas in its orbital neighborhood. Jupiter is born as a gas giant, 100 or more Earth masses of hydrogen and helium wrapped around a core of rock and ice. This model is elegant. It explains why gas giants are found beyond the snow line, where solid material was abundant enough to build a large core quickly. It explains why Jupiter is mostly hydrogen and helium, reflecting the composition of the solar nebula from which the gas was captured. It predicts the existence of a dense, compact core at Jupiter's center, the original seed, and it is broadly consistent with observations of protoplanetary disks around other young stars, which show that the raw materials and conditions for core accretion are common throughout the galaxy. But there is a catch. The solar nebula does not last forever. The gas in a protoplanetary disk is gradually dispersed by the radiation and solar wind from the young star, a process that typically takes between 3 and 10 million years. After that, the gas is gone, and no more gas giants can form. This means Jupiter's core had to grow to 10 Earth masses within the first few million years of the solar system's existence. That is a tight deadline. Some models struggle to grow a core fast enough, particularly if the planetesimals in the disk were small or if the disk was less massive than assumed. The timing constraint is one of the ongoing challenges for core accretion theory. An alternative model, called disk instability, proposes a very different pathway. In this scenario, Jupiter did not form from the bottom up, core first, gas later. Instead, the gas disk itself became gravitationally unstable, developing dense clumps that collapsed directly into gas giant planets, much as the original molecular cloud collapsed to form the Sun. This model does not require a core to form first. The gas giant assembles in one dramatic gravitational collapse, potentially in just a few thousand years, far faster than core accretion allows. Disk instability is attractive because it solves the timing problem, but it has its own difficulties. It requires the disk to be massive and cold, conditions that may not have prevailed everywhere or at all times, and it does not naturally explain the enrichment of heavy elements observed in Jupiter and Saturn, both of which contain more rock, metal, and ice than a pure gas collapse would predict. Core accretion, for all its challenges, does a better job of explaining the heavy element content. The debate between these two models continues, and the truth may involve elements of both. Some theorists have proposed hybrid scenarios, where disk instability creates the initial gas clump and core accretion adds heavy elements afterward. Others have suggested that different giant planets in different systems may form by different mechanisms, with disk instability dominating in massive disks around young, luminous stars and core accretion prevailing in more modest disks like the one that surrounded our own young sun. A third pathway, pebble accretion, has emerged in recent years as a compelling middle ground. Traditional core accretion assumed the growing core swept up large planetesimals, objects kilometers to hundreds of kilometers across. But pebble accretion, developed extensively by Michael Lambrechts and Anders Johansson starting around 2012, proposes that the core grew primarily by capturing small particles, centimeter to meter-sized pebbles, that drifted inward through the gas disk due to aerodynamic drag. The key insight is that pebbles, being small, are strongly affected by the gas drag and can be captured much more efficiently than large planetesimals. A growing core surrounded by gas creates a pressure gradient that funnels drifting pebbles toward it, allowing it to accrete mass at rates far exceeding those of classical planetesimal accretion. Pebble accretion can build a 10 Earth mass core within 1 to 3 million years, comfortably within the lifetime of the gas disk. It elegantly solves the timing problem that plagued classical core accretion without requiring the extreme conditions demanded by disk instability. But pebble accretion introduces new uncertainties about the composition and isotopic signatures of the resulting planet, uncertainties that current measurements cannot fully resolve. The question of how Jupiter formed is not merely an academic exercise. It is connected to the most fundamental question in planetary science. Why do planetary systems look the way they do? Every star in the Milky Way formed with a disk of gas and dust around it. Most of those disks are now gone, dispersed by stellar radiation and winds. But the planets that formed from those disks remain, and the architecture of each planetary system, the number of planets, their masses, their orbits, their compositions, depends critically on how and when the first giant planet formed. Jupiter was the first giant planet in our system. Its formation determined the fate of everything that came after. Consider the enrichment problem in more detail, because it illustrates the difficulty of choosing between formation models. Jupiter's atmosphere is enriched in heavy elements, meaning it contains more carbon, nitrogen, sulfur, argon, and other elements heavier than helium than would be expected if Jupiter were simply a chunk of solar nebula gas captured wholesale. The Galileo probe measured these enrichments directly, finding that carbon, nitrogen, sulfur, argon, krypton, and xenon were all enriched by roughly 2 to 4 times relative to the solar value. This enrichment is a crucial diagnostic. If Jupiter formed by disk instability, collapsing directly from gas, its composition should match the solar nebula closely, with at most modest enrichment from subsequent planetesimal capture. If it formed by core accretion, the heavy elements in the core would mix into the envelope over time, producing a naturally enriched atmosphere. The observed enrichments favor core accretion, but the details are tricky. Why are the noble gases argon, krypton, and xenon enriched to the same degree as carbon and nitrogen? Noble gases do not form ices easily. Argon, in particular, condenses only at extremely low temperatures, below roughly 30 kelvins. For argon to have been delivered to Jupiter in solid form, it must have been trapped in very cold ices, perhaps amorphous water ice or clathrate hydrates formed at temperatures far below those expected at Jupiter's current orbital distance. This suggests that the building blocks of Jupiter came from colder, more distant regions of the solar nebula, or that Jupiter itself formed farther from the Sun than its current position. But the Juno spacecraft told a story that fits neither model cleanly. When Juno arrived at Jupiter in 2016, one of its primary goals was to measure the planet's gravitational field with unprecedented precision. The technique is conceptually simple, but technically demanding. As Juno orbits Jupiter, the planet's gravity accelerates and decelerates the spacecraft by tiny amounts that depend on how mass is distributed inside the planet. By tracking these minute changes in Juno's velocity, measured to a precision of fractions of a millimeter per second using radio signals bounced between the spacecraft and ground stations on Earth, scientists can construct a detailed map of Jupiter's interior mass distribution. If Jupiter had a compact, dense core, the gravitational field would show a specific mathematical signature, a particular set of values for quantities called gravitational harmonics. The data would reveal a concentrated lump of mass at the center. Instead, Juno found something else entirely. The heavy elements inside Jupiter, the rock, metal, and ice that should compose the core, are not concentrated. They are spread out over a vast volume, extending from the center outward to perhaps 30 to 50% of Jupiter's total radius. The core is dilute. The heavy elements are dissolved into the surrounding hydrogen and helium, mixed through a region perhaps 40,000 kilometers across. Scientists call this a fuzzy core. It is as if someone took a ball of rock, heated it, and stirred it into a pot of soup. The ball is gone. Its material is everywhere. The foundation of the planet has been smeared across its interior. This was not what anyone expected. It challenges the simplest version of core accretion, which predicts a compact core that remains intact at the center. If the core formed first and then attracted gas, why is the core now diluted? What force or event could have broken it apart and mixed it outward? Several hypotheses have been proposed, and each one tells a different story about Jupiter's past. The first hypothesis is that the core was always somewhat diffuse. Perhaps the process of gas accretion was not gentle. Perhaps as hydrogen and helium poured onto the growing planet, the infalling gas generated enormous turbulence, stirring the core material and mixing it into the envelope from the very beginning. Computer simulations by several research groups suggest this is plausible if the gas accretion was particularly violent or if the core was not fully solidified when the gas arrived. In this view, Jupiter never had a compact core. The fuzzy structure is the original configuration, a consequence of a chaotic birth. The second hypothesis is more dramatic. It proposes that Jupiter did have a compact core early in its life, but that core was destroyed by a giant impact. In this scenario, another large protoplanet, perhaps 10 to 20 Earth masses, collided head-on with the young Jupiter. The energy of such a collision would have been almost unimaginable. A body 10 times the mass of Earth, moving at perhaps 40 to 50 kilometers per second, striking a planet already hundreds of Earth masses. The kinetic energy of the impact would have been sufficient to shatter and disperse the core material, mixing it outward into the metallic hydrogen mantle. A research team led by Shangfei Liu at Sun Yat-sen University published detailed simulations of this scenario in the journal Nature in 2019. Their models showed that a giant impact could reproduce the dilute core structure observed by Juno, provided the impactor was large enough and the collision occurred within the first few million years of Jupiter's life. This idea that Jupiter was struck by a planet-sized body is not speculation from science fiction. It is a serious scientific hypothesis. published in a top-tier journal, consistent with what we know about the conditions in the early solar system. The inner solar system experienced multiple giant impacts during its formative period. The most famous is the collision between the proto-Earth and a Mars-sized body called Theia. Roughly 4.5 billion years ago, an impact so violent that it partially melted both bodies and flung debris into orbit that eventually coalesced into our moon. If such catastrophic impacts occurred among the rocky inner planets, there is no reason to assume the outer solar system was immune. The early solar system was a shooting gallery, a chaos of protoplanets and debris colliding at tremendous speeds. Jupiter, the largest target, would have been hit repeatedly. The giant impact scenario has further implications that extend beyond Jupiter's core. If a 10 to 20 Earth mass body slammed into Jupiter early in its history, the collision would have released energy equivalent to roughly 10 to the 36th joules, an almost incomprehensible amount of energy, sufficient to heat and partially homogenize a vast volume of the planet's interior. The shock waves from such an impact would have propagated through the entire planet, disrupting any stratified layering and mixing materials that had previously been separated by density. The thermal aftermath would have taken millions of years to dissipate, during which the interior would have been in a state of enhanced convection, stirring and redistributing heavy elements throughout the hydrogen-helium envelope. The fact that the dilute core has survived for 4.5 billion years without fully mixing or fully reconsolidating suggests that some stabilizing mechanism, likely the double diffusive convection mentioned earlier, acts as a brake on further mixing, preserving the fuzzy structure as a kind of fossil imprint of a violent ancient event. And it gets worse. The mystery of Jupiter's interior is not limited to its core. Juno's instruments have revealed that Jupiter's atmosphere is far more complex than the simple banded structure visible in photographs taken from a distance. Beneath the cloud tops, at both poles, enormous cyclonic storms persist in geometric arrangements that no one predicted. At the North Pole, a central cyclone is surrounded by 8 smaller cyclones, arranged in an octagonal pattern, like pearls on a necklace. At the South Pole, a central cyclone is encircled by 5 peripheral cyclones forming a pentagonal shape. Each of these polar cyclones spans thousands of kilometers. Some are as wide as 4,000 kilometers, others as wide as 7,000. They are comparable in scale to the continental United States. They are stable. They persist from one orbit to the next, maintaining their spacing and arrangement with remarkable fidelity. And no one fully understands why. On Earth, cyclonic storms form, intensify, and dissipate over days or weeks. They are transient events driven by the energy of warm ocean water and shaped by the Coriolis force of Earth's rotation. They do not assemble into geometric formations. They do not persist for years. Jupiter's polar cyclones do both. The mechanism that maintains their arrangement, that prevents them from merging into one giant storm or drifting apart and dissipating, remains an open question. Fluid dynamics experiments on Earth have shown that vortices in rotating fluids can spontaneously arrange into polygonal patterns, and some theoretical models have reproduced features similar to Jupiter's polar cyclones. But no model has yet produced a complete, convincing explanation. Jupiter's weather extends far deeper than anyone believed before Juno. The jet streams that produce the visible banded structure are not shallow phenomena. They penetrate to depths of roughly 3,000 kilometers beneath the cloud tops, far deeper than any pre-Juno model predicted. Below that depth, the planet rotates essentially as a rigid body, its rotation rate uniform at every latitude. This transition, from differential rotation in the outer atmosphere to uniform rotation in the deep interior, occurs at the depth where hydrogen becomes electrically conducting enough for the planet's magnetic field to couple the fluid to the overall rotation. The atmosphere and the interior are not separate systems. They are one continuous, churning engine, linked by the physics of metallic hydrogen and the dynamics of magnetic coupling. To put the depth of Jupiter's weather layer in perspective, consider Earth. Our planet's atmosphere is a thin shell, roughly 100 kilometers thick from sea level to the edge of space. The troposphere, the layer where all weather occurs, extends only about 10 to 15 kilometers above the surface. Every cloud, every rainstorm, every hurricane, every blizzard occurs within a layer thinner than the distance between most cities. Jupiter's weather layer is 3,000 kilometers deep. That is roughly the distance from New York to Los Angeles. Imagine a storm system that does not just swirl across the surface, but extends downward through the full width of a continent, reaching into regions where the pressure exceeds tens of thousands of atmospheres and the temperature exceeds thousands of degrees. That is Jupiter's weather. It is not weather as we know it. It is a planetary-scale fluid dynamics phenomenon, driven by forces and occurring at scales that have no parallel on Earth. The Great Red Spot, the most iconic feature on Jupiter, adds yet another layer of puzzle. This anticyclonic storm has been observed since at least 1631, when it may have been noted by the Italian astronomer Giovanni Battista Riccioli, though some historians credit Giovanni Cassini with the first clear observation around 1665. Regardless of the exact start date, the storm has persisted for at least 350 years. No storm on Earth lasts more than a few weeks. Hurricane seasons come and go. Typhoons form and dissolve within days. The Great Red Spot endures across centuries, but it is changing. Over the past 150 years, the Great Red Spot has been shrinking. In the late 1800s, the storm measured roughly 40,000 kilometers across, wide enough to fit 3 Earths side by side. By the early 21st century, it had narrowed to about 16,000 to 17,000 kilometers. It is still larger than Earth, but it has lost more than half its width. Some planetary scientists have speculated that the Great Red Spot could disappear entirely within the next few decades. Others think it may stabilize at a smaller size, reaching a new equilibrium. The truth is that we do not fully understand what powers the storm, what sets its size, or what determines its longevity. We observe it, we measure it, but we cannot yet explain it from first principles. This uncertainty extends to one of the most fundamental questions about Jupiter. How much water does it contain? Water might seem like a minor detail compared to the metallic hydrogen interior and the dilute core. But in the context of planetary formation, water is a tracer of extraordinary importance. The amount of water in Jupiter tells us about the conditions in the solar nebula when the planet formed. It tells us where Jupiter formed, because the abundance of water ice varies with distance from the Sun. More water suggests formation farther from the Sun, where ice was abundant. Less water suggests formation closer in, or a more complex history of mixing and migration. The water content is a signature of Jupiter's birthplace. The Galileo probe, which descended into Jupiter's atmosphere on the 7th of December 1995, was supposed to answer this question. The probe entered the atmosphere at a speed of roughly 47 kilometers per second, the fastest atmospheric entry in the history of spaceflight. It survived the deceleration forces, deployed its parachute, and transmitted data for about 57 minutes as it descended through the clouds. It measured temperature, pressure, wind speed, and chemical composition. But by a stroke of terrible luck, the probe entered what turned out to be a hotspot, an unusually dry, cloud-free region of downwelling atmosphere. Hotspots are like deserts in Jupiter's atmosphere, regions where air is sinking from high altitude, warming and drying as it descends. The water measurement the Galileo probe returned was far lower than expected, almost certainly not representative of the planet as a whole. Juno has attempted to fill this gap. Its microwave radiometer, an instrument that can peer through the cloud tops and sense the thermal emission of the atmosphere at various depths, has been measuring the water abundance at different latitudes. The results, published in several papers starting in 2020, have been both illuminating and perplexing. Near Jupiter's equator, the water abundance appears to be roughly 2 to 4 times greater than the solar value, meaning Jupiter has 2 to 4 times more oxygen relative to hydrogen than the Sun does. But the water abundance is not uniform. It varies from one latitude to another, and the polar regions appear to be drier than the equator. The global average remains uncertain, and the global average is what matters for constraining formation models. If Jupiter formed at the snow line, roughly 3.5 to 5 astronomical units from the Sun, it should have captured a certain amount of water ice leading to a particular water abundance in the final planet. If it formed farther out, at 7 or 10 or 15 astronomical units, where water ice was even more abundant, the water content should be higher. And if Jupiter migrated from a more distant birth orbit to its current position, the water content should reflect the conditions at the original formation site. The water abundance is a key to Jupiter's origin story, and we still do not have a definitive measurement. This matters enormously because the question of where Jupiter formed connects to the most radical and far-reaching model of solar system evolution ever proposed, the Grand Tack hypothesis. The Grand Tack, published by Kevin Walsh, Alessandro Morbidelli, and colleagues in 2011, proposes that Jupiter did not simply form at 5 astronomical units and stay there. It migrated. In the early solar system, when the gas disk was still present, Jupiter interacted with the surrounding gas through a process called Type II migration. The gravitational interaction between Jupiter and the gas disk caused the planet to spiral slowly inward toward the Sun. In the Grand Tack scenario, Jupiter migrated all the way inward to about 1.5 astronomical units, roughly the orbit of Mars. 1.5 astronomical units. That is deep into the inner solar system, in the region where the terrestrial planets were just beginning to form. At that point, Saturn, which had been forming farther out, also migrated inward and caught up with Jupiter. When the two giants reached a specific orbital configuration, a 2 to 3 mean motion resonance, their combined gravitational interaction with the gas disk reversed their migration. They turned around. They migrated back outward, Jupiter settling at roughly its current distance of 5.2 astronomical units, Saturn at 9.5. The implications of this scenario are staggering. If Jupiter came that close to the Sun, it would have ploughed through the region where the terrestrial planets were forming. It would have scattered or absorbed planetesimals, drastically reducing the supply of material available to build the inner planets. This is one possible explanation for why Mars is so small. Mars has only about 1/10 the mass of Earth. For decades, this was a puzzle. Standard models of planet formation predicted that Mars should be comparable in size to Earth or Venus. The Grand Tack offers an explanation. Jupiter truncated the supply of building material in the Mars-forming region during its inward migration, starving Mars of the mass it needed to grow larger. The Grand Tack also explains the structure of the asteroid belt, which lies between Mars and Jupiter at roughly 2 to 3.5 astronomical units. The belt is sparse, containing only about 4% of the Moon's mass in total. It is also compositionally mixed, containing both rocky asteroids, similar to the material in the inner solar system, and more water-rich carbonaceous asteroids, similar to material from the outer solar system. The Grand Tack predicts exactly this mixing. As Jupiter moved inward and then outward, it scattered both inner and outer solar system material into the belt region, creating the mixed population we observe. But here's what makes this truly terrifying. If the Grand Tack hypothesis is correct, then our solar system's current arrangement, the arrangement that allowed Earth to form, to acquire water, to develop life, is the product of a near catastrophe. Jupiter nearly destroyed the inner solar system. It swept through the terrestrial planet-forming region, scattering material, disrupting orbits, and fundamentally altering the course of planet formation. And then, by a fortunate gravitational interaction with Saturn, it reversed course and retreated. The inner solar system survived, Earth formed, life arose. But the margin may have been thin, a slightly different timing, a slightly different Saturn, and the outcome could have been very different. Understanding Jupiter has been one of the longest and most humbling journeys in the history of planetary science. For more than 400 years, our knowledge evolved in stages, each stage revealing new wonders but also deeper puzzles. Each spacecraft mission, each telescopic campaign, each theoretical model has encountered the same frustrating reality. Jupiter refuses to be simple. It resists our categories. It defies our expectations, and it punishes overconfidence with surprise. The first serious observations of Jupiter were made by Galileo Galilei in the winter of 1609 to 1610 using a refracting telescope of his own design with a magnification of roughly 20 times. Through this modest instrument, Galileo saw things no human had ever seen. He saw 4 points of light near Jupiter that changed position from night to night. He recognized them as satellites, moons orbiting another planet. This was a conceptual earthquake. It meant the Earth was not the only center of orbital motion in the cosmos. Galileo published his findings in a book called Sidereus Nuncius, the Starry Messenger, in March of 1610. The 4 moons he discovered, Io, Europa, Ganymede, and Callisto, are still called the Galilean moons in his honor. For the next 3 centuries, our knowledge of Jupiter grew slowly. Astronomers observed the banded structure of its atmosphere, tracked the Great Red Spot, measured its rotation period, and estimated its mass and size. By the early 20th century, we knew Jupiter was a giant planet composed mainly of light gases, orbiting the Sun at about 5 astronomical units. We knew it had at least a dozen moons. We knew the Great Red Spot was a persistent atmospheric feature. But we knew almost nothing about its interior, its magnetic field, or its detailed atmospheric composition. The space age changed everything. The first spacecraft to visit Jupiter was Pioneer 10, launched in March of 1972 by NASA from Cape Canaveral. Pioneer 10 was a simple, hardy craft weighing about 260 kilograms and powered by plutonium-fueled radioisotope thermoelectric generators. Since solar panels would be useless at Jupiter's distance from the Sun, it crossed the asteroid belt, the first human-made object to do so, and reached Jupiter in December of 1973, passing within roughly 130,000 kilometers of the cloud tops. Pioneer 10 was a scout, and its findings were sobering. The radiation environment near Jupiter was far more intense than any model had predicted. The magnetic field trapped charged particles from the solar wind and from Io's volcanic outgassing, accelerating them to energies that temporarily blinded some of the spacecraft's instruments. The radiation dose at Pioneer 10's closest approach was roughly 1,000 times the lethal dose for a human. This was the first clear warning that Jupiter is not a place that welcomes visitors. Pioneer 10 also returned the first close-up images of Jupiter's cloud tops, confirming the banded structure and revealing details invisible from Earth. It measured the planet's thermal emission, finding that Jupiter radiates about 1.7 times more energy than it receives from the Sun. This excess energy comes from the planet's interior, the residual heat of formation, and the slow gravitational contraction that continues today, 4.5 billion years after Jupiter was born. Pioneer 11 followed in December of 1974, approaching Jupiter from a different trajectory that carried it over the polar regions. It provided the first views of Jupiter's poles, which looked very different from the equatorial and mid-latitude bands that dominate Earth-based observations. Pioneer 11 also confirmed the intense radiation and measured the magnetic field in more detail, finding it to be complex and asymmetric, not the simple dipole that a naive model would predict. But the Pioneers were flybees, brief encounters lasting just a few days. The spacecraft that truly opened our eyes to the Jovian system were the twin Voyagers. Voyager 1 reached Jupiter in March of 1979. Voyager 2 arrived 4 months later, in July. These 2 spacecraft carried far more sophisticated instruments than the Pioneers, including high-resolution cameras capable of returning detailed images of Jupiter's atmosphere and moons. Together, the Voyagers transformed our understanding of the Jovian system in ways that are still felt today. Voyager 1 made perhaps the single most stunning discovery of the entire mission: active volcanoes on Io. The images showed enormous plumes of sulfur and sulfur dioxide erupting hundreds of kilometers above Io's surface, the material falling back in graceful arcs and coating the landscape in vivid yellows, oranges, and reds. Before Voyager, Io was expected to be a dead, cratered world similar to our moon. Instead, it was the most geologically active body in the solar system, its entire surface being constantly recycled by volcanic eruptions. The heat source was identified as tidal heating, the gravitational stretching and squeezing of Io as it orbits Jupiter in the company of the other Galilean moons. The orbital resonance between Io, Europa, and Ganymede, a relationship in which their orbital periods are locked in a ratio of 1 to 2 to 4, prevents their orbits from circularizing. The slight orbital eccentricity means Io is alternately stretched and compressed as it approaches and recedes from Jupiter, generating internal friction that heats its interior and drives the volcanism. Voyager 2 provided the first detailed images of Europa's surface. What it revealed was unlike anything in the solar system. Europa's surface was smooth, almost entirely devoid of impact craters, covered in a network of dark lines that crossed and intersected like veins on a leaf. The smoothness indicated a young surface, one being continuously renewed. The cracks suggested movement, as though a solid crust was floating on something fluid beneath. The idea that Europa might have a subsurface ocean of liquid water began to take shape in the minds of planetary scientists. If confirmed, such an ocean would make Europa one of the most promising places in the solar system to search for extraterrestrial life. The Voyagers also discovered something entirely unexpected. Jupiter has rings. Thin, faint, and composed not of ice like Saturn's brilliant rings, but of microscopic particles of rock and dust. Jupiter's ring system had been invisible from Earth. The main ring is a narrow band roughly 6,400 kilometers wide and only about 30 kilometers thick, orbiting within Jupiter's equatorial plane. Inside the main ring lies a thick, diffuse halo of particles extending down toward the cloud tops, and outside it lie two faint gossamer rings associated with the tiny moons Amalthea and Thebe. The ring particles are continually replenished by micrometeorite impacts on these small inner moons, which blast material off their surfaces and into orbit around Jupiter. Without this constant replenishment, Jupiter's rings would dissipate within perhaps 10,000 years. They are not ancient features. They are dynamic, transient, maintained by an ongoing process of destruction and renewal. The discovery of Jupiter's rings demonstrated that ring systems are not unique to Saturn. They are a common feature of giant planets, appearing in different forms around all four of the outer planets in our solar system. The Voyagers turned their cameras on Ganymede and Callisto as well. Ganymede's surface revealed a patchwork of two distinct terrain types: ancient, heavily cratered dark regions, and younger, lighter regions, crossed by complex systems of grooves and ridges, some extending hundreds of kilometers and standing several hundred meters high. These grooved terrains suggested a history of tectonic activity, crustal stretching and deformation driven by internal forces. This was remarkable for a moon long assumed to be geologically dead. Callisto, the outermost Galilean moon, presented a stark contrast. Its surface was uniformly ancient, saturated with impact craters, showing no evidence of tectonic or volcanic activity. Callisto appeared to be the most geologically primitive large body in the solar system, a relic of the early bombardment era, its surface unchanged for billions of years. The contrast between Ganymede's partial resurfacing and Callisto's frozen antiquity raised fundamental questions about why two moons of similar size and composition could have such different geological histories. The answer, again, lay in orbital dynamics and tidal heating, in the subtle but powerful effects of Jupiter's gravity on the worlds that orbit it. The Voyager missions also documented the complexity of Jupiter's atmosphere with unprecedented clarity. They captured images of swirling vortices, turbulent eddies, wave patterns, and cloud formations that looked almost organic in their complexity. The atmosphere was not a simple system of uniform bands. It was a three-dimensional fluid dynamics laboratory, with structures at every scale from continent-sized storms to tiny wisps of cloud smaller than individual states. The Voyagers measured wind speeds in excess of 600 kilometers per hour. They tracked the evolution of individual storms over weeks, and they revealed that the atmospheric dynamics were driven not primarily by solar heating, as on Earth, but by the planet's internal heat. Jupiter is its own heat engine, powered from within. After the Voyagers, the next major step was the Galileo mission, which arrived at Jupiter in December of 1995 after a 6-year journey from Earth. Galileo was the first spacecraft to orbit Jupiter, remaining in the Jovian system for nearly 8 years, until September of 2003, when it was deliberately sent into Jupiter's atmosphere to avoid any possibility of contaminating Europa's ocean with Earth microbes. Galileo carried an atmospheric probe that separated from the orbiter 5 months before arrival and plunged into Jupiter's atmosphere on December 7, 1995. The probe entered at a blistering speed of roughly 47.4 kilometers per second, experiencing deceleration forces of approximately 230 times the force of gravity on Earth's surface. It survived this violent entry, deployed a parachute, and transmitted data for about 57 minutes as it descended through the cloud layers. It measured temperature, pressure, wind speed, and atmospheric composition before succumbing to the crushing pressure at a depth of approximately 158 kilometers below the cloud tops. The probe's data was invaluable but, as discussed earlier, compromised by its entry point. It descended into a hotspot, a dry, cloud-free downdraft where the atmosphere was depleted of water and other condensable species. The water measurement was anomalously low, likely not representative of Jupiter as a whole. This was a bitter disappointment. The water abundance was one of the key measurements the mission was designed to obtain, and the single probe had entered precisely the wrong location. It was as though an alien spacecraft, descending to study Earth's climate, had landed in the Sahara Desert and concluded that the planet was arid. The Galileo orbiter, however, made extraordinary contributions. Its magnetometer and plasma instruments mapped Jupiter's magnetic field and radiation environment in 3 dimensions. Its near-infrared spectrometer studied the compositions of the Galilean moon's surfaces, and its gravity science experiment provided the first detailed measurements of Jupiter's internal mass distribution. Though these measurements were not precise enough to determine the structure of the core, Galileo's most profound discovery was the confirmation that Europa almost certainly has a subsurface ocean. The evidence came from the magnetometer. As Europa orbits Jupiter, it moves through Jupiter's powerful magnetic field, which varies in direction and strength at Europa's location because of Jupiter's tilted magnetic axis. If Europa were a solid body of rock and ice, it would not respond to these magnetic variations. But Galileo detected an induced magnetic field around Europa, a secondary field generated by electrical currents flowing in a conducting layer beneath the surface. The most natural explanation for such a conducting layer is a salty liquid water ocean beneath the ice. The ocean would need to be global, at least several kilometers deep, and contain enough dissolved salts to conduct electricity. Subsequent analysis suggested the ocean could be 60 to 150 kilometers deep, containing 2 to 3 times the volume of water in all of Earth's oceans. The Galileo mission also revealed the full horror of Jupiter's radiation environment. The spacecraft's instruments degraded steadily over the course of the mission as energetic particles battered its electronics. The total radiation dose accumulated by Galileo exceeded 4 times its design specification. Several instruments failed or suffered reduced performance. The tape recorder, essential for storing data during close moon flybys when the spacecraft could not simultaneously point its antenna at Earth, jammed early in the mission, forcing engineers to develop creative workarounds that reduced data return but kept the mission alive. The struggle against Jupiter's radiation was a constant theme of the Galileo mission, a reminder that Jupiter is not merely inhospitable but actively hostile to the machines we send there. Every spacecraft that visits Jupiter must be designed from the ground up to survive conditions that would destroy ordinary electronics within hours. The gap between Galileo and Juno, roughly 13 years from Galileo's end of mission in 2003 to Juno's arrival in 2016, was a period of theoretical ferment. The scientific community digested Galileo's results, developed competing models for Jupiter's interior and formation, and designed the instruments and mission profile that would become Juno. During this period, the Cassini spacecraft, en route to Saturn, made a gravity assist flyby of Jupiter in December of 2000 and returned valuable data on Jupiter's magnetosphere and atmospheric dynamics. New Horizons, on its way to Pluto, also flew past Jupiter in February of 2007, returning stunning images and studying the Jovian magnetotail. But neither of these missions was designed for detailed Jupiter science. The community waited, argued, and planned, and when Juno finally arrived, the wait proved justified. Then came Juno, and Juno changed everything again. Juno was launched in August of 2011 and arrived at Jupiter in July of 2016. entering a highly elliptical polar orbit that brought it as close as about 4,200 kilometers above the cloud tops at each closest approach, called perigove, before swinging out to distances of over 8 million kilometers. This orbit was carefully designed. By flying close over the poles, Juno passed beneath the most intense radiation belts, which are concentrated near the equator. This reduced the radiation exposure to the spacecraft's electronics, which were housed in a titanium vault weighing about 180 kilograms, designed to shield sensitive components from Jupiter's punishing particle environment. The orbital insertion itself was one of the most nerve-wracking events in the history of planetary exploration. On the night of July 4, 2016, Juno fired its main engine for 35 minutes to slow itself enough to be captured by Jupiter's gravity. During this burn, the spacecraft was entirely autonomous. Radio signals take 48 minutes to travel one way between Jupiter and Earth, making real-time control impossible. The mission team at the Jet Propulsion Laboratory in Pasadena could only wait, watching telemetry that was already nearly an hour old, hoping that every command had been executed correctly. A failure of the engine, a miscalculation in timing, a software glitch, and the spacecraft would have sailed past Jupiter into the void. $2.8 billion and 5 years of travel wasted. The engine fired perfectly, Juno entered orbit, and the science began. The original mission plan called for Juno to transition from its initial 53-day orbit into a 14-day orbit, allowing more frequent close approaches. But a problem with 2 helium check valves in the fuel system made engineers nervous about performing the required engine burn. After careful analysis, NASA decided to keep Juno in the longer 53-day orbit rather than risk a burn that might damage the propulsion system. This decision reduced the frequency of science passes but extended the overall mission duration, and Juno has been making the most of each perigove ever since. Juno carries 9 scientific instruments. The Gravity Science Experiment uses the spacecraft's radio link to Earth to measure tiny Doppler shifts in the signal, revealing the distribution of mass inside Jupiter. The microwave radiometer observes the thermal emission of the atmosphere at 6 different wavelengths, allowing scientists to probe the temperature and composition of the atmosphere from the cloud tops down to hundreds of kilometers depth. The magnetometer measures the magnetic field in 3 dimensions. JunoCam, a visible light camera originally included for public outreach, has returned stunning images of Jupiter's clouds, polar cyclones, and atmospheric detail that no previous mission could have captured. The results from Juno have reshaped our understanding of Jupiter in fundamental ways. Let us examine the 5 most important findings and wrestle with what each one means. First, the dilute core. Juno's gravity measurements have firmly established that Jupiter does not have a compact core of rock and metal at its center. Instead, the heavy elements are spread over a large volume, mixed into the hydrogen-helium interior. The numbers are striking. Current models estimate the dilute core contains between 7 and 25 Earth masses of heavy elements, smeared across a region that extends from the center to roughly 30 to 50% of Jupiter's total radius, a volume comparable to that of several Earths. This finding has generated multiple competing explanations, from primordial mixing during gas accretion to destruction by giant impact. Neither explanation is fully satisfactory. If convective mixing eroded a compact core, why hasn't the erosion continued to completion over 4.5 billion years? If a giant impact shattered the core, why is the dilute structure so stable? The answer may involve double diffusive convection, a process in which gradients in both temperature and composition create stable layers that resist overturning. But this process is notoriously difficult to model in the extreme conditions of a giant planet interior. Second, the deep weather. Before Juno, most models assumed Jupiter's jet streams and banded structure were shallow phenomena, confined to the outer few hundred kilometers of atmosphere, driven by solar heating and the planet's rotation. Juno's gravity data shattered this assumption. The jet streams penetrate to depths of roughly 3,000 kilometers below the cloud tops. This means the visible bands and zones are not painted onto the surface. They are manifestations of deep-seated flows rooted in the transition zone between molecular and metallic hydrogen. Below 3,000 kilometers, the increasing electrical conductivity of hydrogen allows Jupiter's magnetic field to break the differential rotation, imposing a more uniform rotation on the deep interior. The 3,000-kilometer depth marks a boundary between two regimes: the weather layer above and the magnetically dominated interior below. The discovery that Jupiter's weather extends 3,000 kilometers deep has forced a complete rethinking of atmospheric dynamics on giant planets. Earth's weather is confined to a thin troposphere roughly 10 to 15 kilometers deep. Jupiter's weather layer is 200 times deeper. The energy driving Jupiter's weather comes not from the sun, but from the planet's interior. It's slowly dissipating birth heat. This means Jupiter's atmospheric dynamics are fundamentally different from Earth's, driven from below rather than above, powered by internal heat rather than external radiation. Models that treat Jupiter's atmosphere as a thin layer on top of a passive interior are wrong. The atmosphere and the interior are coupled, interacting through heat transport, magnetic forces, and fluid dynamics. Third, the polar cyclones. Juno's observations of Jupiter's poles were among the most visually spectacular and scientifically puzzling results of the entire mission. At the North Pole, 8 cyclones surround a central cyclone in an octagonal formation. Each peripheral cyclone is roughly 4,000 to 4,600 kilometers in diameter. At the South Pole, 5 cyclones encircle a central storm in a pentagonal arrangement, each spanning roughly 5,400 to 7,400 kilometers. These formations are stable over the entire duration of Juno's mission, maintaining their spacing and geometry orbit after orbit. But here's the problem. Why 8 at the north and 5 at the south? Why not the same number at both poles? Why are the southern cyclones larger than the northern ones? And what prevents them from merging? On Earth, cyclonic storms merge when they approach each other closely, a process called the Fujiwara effect. Jupiter's polar cyclones defy this tendency. They maintain their separation despite being packed closely together at the poles. Theoretical models suggest that the anticyclonic shear surrounding each cyclone creates a kind of buffer zone, preventing merger. But the details depend on parameters like the depth of the cyclones, the stratification of the atmosphere, and the local heat flux from the interior, parameters that are not well constrained. Fourth, the magnetic field. Juno's magnetometer has revealed that Jupiter's magnetic field is far more complex than a simple dipole. The field has strong higher-order components, meaning it has bumps, dips, and asymmetries that cannot be described by a single bar magnet model. One particularly striking feature is a region of concentrated magnetic flux in the northern hemisphere, informally dubbed the Great Blue Spot. This anomaly is a localized patch where the magnetic field is unusually strong and has the opposite polarity from the surrounding field. It may be produced by a specific flow pattern in the metallic hydrogen dynamo, perhaps a plume of electrically conducting fluid rising or sinking in a particular location. The Great Blue Spot appears to be slowly drifting westward, suggesting it is tied to a deep interior flow that does not rotate at exactly the same rate as the rest of the planet. The complexity of Jupiter's magnetic field tells us that the dynamo, the process generating the field, is not simple. On Earth, the dynamo operates in the liquid iron outer core, a relatively thin shell, roughly 2,200 kilometers thick, sitting atop a solid inner core. The convective motions in this liquid iron layer generate the electrical currents that sustain Earth's magnetic field. The process is called a self-sustaining geodynamo, and while the basic physics is understood, the details remain extraordinarily complex. Earth's magnetic field reverses polarity at irregular intervals, sometimes every few 100,000 years, sometimes not for tens of millions of years. The dynamo is chaotic, sensitive to conditions, difficult to predict. Jupiter's dynamo is even more complex. It operates in the metallic hydrogen layer, a region far thicker and far more massive than Earth's liquid iron core. The transition from molecular to metallic hydrogen is not a sharp boundary, but a gradual change, meaning the dynamo region does not have well-defined edges. The dilute core may play a role in the dynamo as well. either as a heat source driving convection or as a compositional barrier inhibiting certain flow patterns. The fact that Jupiter's magnetic field has such strong higher-order components suggests that the flow patterns generating the field are complex, with small-scale structures and asymmetries that would be invisible in a simple dipole model. Understanding Jupiter's dynamo is essential for understanding the dynamos of all giant planets, including the ice giants Uranus and Neptune, whose magnetic fields are tilted at large angles to their rotation axes and offset from their centers, suggesting entirely different dynamo geometries. The study of planetary dynamos is a comparative science, and each planet's field provides constraints on the others. Fifth, the question of formation and migration. The Grand-Tack hypothesis, proposed by Kevin Walsh and colleagues in 2011, remains one of the most influential models of solar system evolution. It proposes that Jupiter migrated inward to about 1.5 astronomical units before being pulled back outward by a gravitational interaction with Saturn. But the Grand-Tack is not the only game in town. The Nice model, developed in 2005 by a team including Hal Leveson, Alessandro Morbidelli, and Cleomenes Tiganis, proposed that the giant planets formed in a more compact configuration and underwent a period of dynamical instability that scattered them into their current orbits. The original Nice model placed this instability roughly 700 million years after the solar system formed, coinciding with the late heavy bombardment, a period of intense cratering on the Moon and the inner planets. But more recent work has pushed the instability earlier, perhaps to within the first 100 million years, or even the first 10 million years. Other models, such as the early instability model and the pebble accretion model, offer alternative pathways. Pebble accretion, in particular, has gained significant traction in recent years. Instead of growing by capturing large planetesimals, Jupiter's core may have grown primarily by sweeping up small pebbles, centimeter to meter-sized particles that drifted inward through the gas disk due to aerodynamic drag. Pebble accretion is much faster than planetesimal accretion and can grow a 10 Earth mass core within the 1 to 3 million year window required by the lifetime of the gas disk. But pebble accretion has its own challenges, including the difficulty of explaining the detailed composition of Jupiter's atmosphere, which shows enrichments in certain elements that are hard to produce with pebbles alone. The pebble accretion model also makes specific predictions about the isotopic ratios of certain elements in Jupiter's atmosphere, particularly nitrogen. Nitrogen in Jupiter's atmosphere is enriched by roughly 3 to 4 times relative to the solar value. If nitrogen is delivered as ammonia ice frozen onto pebbles, the isotopic signature would differ from nitrogen delivered as molecular nitrogen gas trapped in very cold amorphous ice, which would require formation temperatures below roughly 30 kelvins. The Galileo probe measured the nitrogen isotopic ratio, and the result was consistent with delivery by ice from very cold regions, perhaps beyond the orbit of Saturn. This suggests that the building blocks of Jupiter's core came from a wide range of distances in the solar nebula, not just the immediate neighborhood of the snowline. Each model explains some observations and struggles with others. Core accretion explains the heavy element enrichment, but has trouble meeting the timing constraint. Disk instability meets the timing constraint, but does not naturally produce enrichment. Pebble accretion is fast and can produce enrichment, but its predictions for specific isotopic ratios do not always match measurements. The Grand-Tack explains the small mass of Mars and the mixed composition of the asteroid belt, but requires a finely tuned interaction between Jupiter and Saturn. The Nice model explains the current orbits of the outer planets, but its timing is debated. No single model accounts for everything. The territory is uncertain. What all of these models share is complexity. None of them produces a clean, simple narrative. Each one involves specific assumptions about the initial conditions of the solar nebula, the timing of various events, and the interactions between multiple forming planets. And each one produces predictions that can be tested, at least in principle, by future missions and observations. But the current state of affairs is one of productive confusion. We have multiple plausible stories for Jupiter's origin, and we do not yet have enough data to choose definitively among them. the Juno mission continues to collect data, now in an extended mission phase that focuses on Jupiter's northern hemisphere and several of its smaller moons. The Europa Clipper spacecraft, launched by NASA in October of 2024, will conduct dozens of flybys of Europa beginning in the late 2020s, using radar, magnetometry, and spectroscopy to characterize the icy moon's subsurface ocean. The JUICE mission, launched by the European Space Agency in April of 2023, is en route to the Jovian system and will arrive in 2031, spending several years studying Ganymede, Callisto, and Europa. These missions represent humanity's most ambitious effort yet to understand the Jovian system. But even their combined data will not resolve all the mysteries. The interior of Jupiter will remain inaccessible to direct sampling. The conditions in the metallic hydrogen layer will remain beyond the reach of any probe we can currently build. And the events that shaped Jupiter's early history, the formation of its core, the accretion of its gas envelope, the possible giant impact, the migration through the inner solar system, all of these occurred more than 4 billion years ago and left only indirect traces in the planet's present-day structure. We are reading a palimpsest. The original text has been partially overwritten by billions of years of subsequent evolution. The challenge is to reconstruct the original from the fragments that remain. It is a challenge that has occupied some of the finest minds in planetary science for decades, and it is a challenge that remains, in the most fundamental sense, unmet. Here is the reality that emerges when you take all of these findings together and sit with them quietly. Jupiter is not a finished object. It is not a stable, settled world that formed once and has remained the same ever since. Jupiter is a process, an ongoing, evolving, 4.5 billion-year-old process that has not yet reached equilibrium. It is still cooling, still contracting, still radiating more heat than it receives. Its interior is still evolving, with heavy elements slowly settling or being redistributed by convective currents. Its magnetic field is still changing, drifting, rearranging itself, as the dynamo in the metallic hydrogen layer shifts. Its storms are still forming, merging, splitting, and disappearing. The Great Red Spot is shrinking. The polar cyclones are maintaining their geometry through mechanisms we cannot yet explain. When you look at Jupiter through a telescope, you are not looking at a static body. You are looking at something in motion, something alive, in the sense that a river is alive, always moving, always changing, always shaped by forces acting at scales we can barely comprehend. Let that sink in. We tend to think of planets as fixed objects, like furniture in a room. They have their assigned positions, their known characteristics, their predictable behaviors. We learn them in school as a list. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, each with a set of facts. Jupiter is the largest. Jupiter has the Great Red Spot. Jupiter has many moons. These facts are true, but they are snapshots, freeze frames of a moving picture, and the moving picture is stranger than any snapshot can convey. Consider what this means for the concept of planetary identity. When we say the word Jupiter, what exactly are we referring to? The cloud tops, which are the only part visible in photographs. They are a thin skin, a few hundred kilometers of atmosphere, stretched over a world 143,000 kilometers across. The atmosphere, which extends thousands of kilometers deep, it is a churning, layered fluid, different in composition and behavior at every depth. The metallic hydrogen layer, which generates the magnetic field, it is a sea of liquid metal, unlike anything on Earth, occupying the vast majority of the planet's volume. The dilute core, a smeared-out remnant of the original seed from which the planet grew. All of these are Jupiter. None of them alone is Jupiter. The planet is the totality of its layers, its processes, its history, its ongoing evolution. And that totality is something we have only begun to map. There is a philosophical temptation to view Jupiter as a kind of miniature star, a body that almost crossed the threshold into stellar ignition, a failed sun hovering at the edge of nuclear fusion. This narrative is common in popular science, and it captures the imagination, but it is misleading. If you added roughly 80 times more mass to Jupiter, you might push it past the threshold for sustained hydrogen fusion, and it would become a red dwarf star, the smallest and dimmest class of stellar objects. But 80 Jupiters is a vast amount of mass. Jupiter is nowhere close to being a star. It is not on the verge. It is not teetering on the edge. It is firmly, unambiguously a planet. The most massive planet in our system, with a mass 1,000th that of the Sun, but a planet all the same. What Jupiter does do, however, is blur the boundaries between categories in ways that make scientists uncomfortable. Between the largest planets and the smallest stars lies a class of objects called brown dwarfs, bodies with masses between roughly 13 and 80 times Jupiter's mass. Brown dwarfs are too large to be called planets by any conventional definition, but too small to sustain hydrogen fusion in their cores. They briefly fused deuterium, a heavier isotope of hydrogen, in their youth, but this energy source runs out quickly. After that, they simply cool and fade, slowly dimming over billions of years. Brown dwarfs share many characteristics with Jupiter: internal heat sources, powerful magnetic fields, complex atmospheric dynamics, compositions dominated by hydrogen and helium. Some brown dwarfs have been discovered with bands and storms resembling Jupiter's. Others have been found orbiting stars in planetary configurations. The boundary between the largest planets and the smallest brown dwarfs is a matter of mass, not of kind. Nature does not draw sharp lines. We do. The study of brown dwarfs has, in fact, deepened our understanding of Jupiter precisely because they represent what Jupiter might have become with more mass. Observations from the Spitzer Space Telescope and ground-based infrared observatories have revealed that brown dwarfs exhibit weather patterns strikingly reminiscent of Jupiter's, with patchy cloud cover, periodic brightness variations, suggesting rotating storm systems, and atmospheric compositions that change with altitude. Some brown dwarfs show signs of silicate clouds, clouds made of vaporized rock condensing at temperatures far beyond anything in Jupiter's atmosphere, but obeying the same physical principles. The atmospheric dynamics of Jupiter and brown dwarfs form a continuum, and models developed for one inform our understanding of the other. When we study Jupiter, we are studying the low-mass end of a class of objects that spans a factor of 100 in mass, from one Jupiter mass to nearly 100 Jupiter masses, all governed by the same fundamental physics of hydrogen-dominated interiors, convective energy transport, and atmospheric fluid dynamics. There is an even subtler point here that deserves attention. Jupiter radiates roughly 1.7 times more energy than it receives from the Sun. Brown dwarfs radiate entirely from internal reserves, receiving negligible energy from any host star. The difference is quantitative, not qualitative. Jupiter is already, in a meaningful sense, self-luminous. It glows in the infrared. It produces its own light, however faint, from its own internal heat. If you could see in the infrared, Jupiter would be a dim, warm ember against the cold backdrop of space, radiating heat it has carried since its birth. This self-luminosity connects Jupiter not to the terrestrial planets, which are thermally passive bodies heated primarily by their stars, but to the brown dwarfs and even the stars themselves, which generate their luminosity from internal sources. Jupiter is, in this precise and measurable sense, more star-like than planet-like in its energy budget. The categorization as a planet is not wrong, but it is incomplete. It misses something fundamental about what Jupiter is doing physically right now in the present moment, slowly cooling, slowly contracting, slowly releasing the gravitational energy stored during its formation. This is not science fiction. This is the current state of planetary science. Jupiter exists at one end of a continuum that stretches from terrestrial planets like Earth, through ice giants like Uranus and Neptune, through gas giants like Jupiter and Saturn, through brown dwarfs, and ultimately to the smallest stars. Where you draw the boundaries on that continuum is a matter of convention. Nature itself is continuous. Let that sink in. Now consider Jupiter's role not merely as an object, but as an agent, an actor in the drama of our solar system's history. Jupiter did not passively form and sit in its orbit. It actively shaped the solar system around it. The gravitational influence of Jupiter has been the dominant non-solar force in the solar system for 4.5 billion years. Every asteroid has felt its pull. Every comet has been nudged, redirected, or flung. Every planet's orbit bears the imprint of Jupiter's mass. The solar system we inhabit is not the solar system that would have existed without Jupiter. It is Jupiter's solar system remade in the image of its gravity, carrying the fingerprints of its mass and its migration in every orbit, every resonance, every gap, and every surviving world. And that influence has not been uniformly benign. On one hand, Jupiter has been credited as a cosmic shield. The idea, popularized by George Wetherill in a landmark 1994 paper, is that Jupiter's gravity deflects or captures potentially dangerous comets and asteroids before they can reach the inner solar system. In this view, Jupiter is a bodyguard, a protector, shielding Earth from catastrophic impacts and thereby allowing complex life to develop in peace. The spectacular collision of comet Shoemaker-Levy 9 with Jupiter in July of 1994 seemed to illustrate this protective role. The comet, torn apart by Jupiter's gravity during a previous close approach, fell into the planet's atmosphere as a string of 21 fragments over the course of 6 days, producing enormous dark scars visible even in amateur telescopes. The largest impact released energy equivalent to roughly 6 million megatons of TNT. If those fragments had hit Earth, the consequences would have been extinction level. But the shield hypothesis is more complicated than it first appears. Research published after Wetherill's original paper has shown that Jupiter's gravitational influence is not a simple deflection mechanism. In many dynamical simulations, Jupiter actually increases the rate of cometary impacts on the inner planets by perturbing the orbits of objects in the Oort cloud and the Kuiper belt, sending them onto trajectories that cross Earth's orbit. A study by Jonathan Horner and Barry Jones, published in 2008, modeled solar systems with Jupiter-like planets of varying masses and found that the relationship between Jupiter's mass and Earth impact rates is complex and nonlinear. In some configurations, removing Jupiter reduced the impact rate on Earth. In others, it increased it. The net protective effect of Jupiter depends sensitively on the specific orbital architecture, and for our particular solar system, the balance is ambiguous. Jupiter's role in the delivery of water and organic molecules to the early Earth adds another dimension. Some models suggest that Jupiter's gravitational stirrings scattered water-rich asteroids and comets from the outer solar system inward, providing Earth with the water that fills its oceans and the carbon compounds that form the basis of life. Without Jupiter, Earth might have been a dry, barren world, but other models suggest that Jupiter's migration through the inner solar system, if the Grand Tack scenario is correct, disrupted the reservoir of water-rich material and reduced the total delivery. Jupiter may have simultaneously given Earth some of its water and taken away some of its potential water. The net effect remains uncertain. The deeper truth is that Jupiter's influence on the habitability of the inner solar system is not a simple story. It is a story of contingency, of specific initial conditions, of chaotic dynamics that could have gone differently with even slight changes. A Jupiter formed 2 million years earlier might have migrated farther inward. A Jupiter formed in a slightly more massive disk might have grown larger, destabilizing Saturn's orbit and scattering the outer planets into the interstellar medium. A Jupiter with a slightly different core mass might have undergone a different migration history, producing a different asteroid belt, a different Mars, a different Earth. We are the product of a specific Jupiter, a specific mass, a specific orbit, a specific migration history, a specific set of gravitational interactions that played out over billions of years. Change any of these parameters, and the outcome changes, perhaps subtly, perhaps catastrophically. The Earth we know, with its oceans and its atmosphere and its biosphere, is a contingent outcome, dependent on factors that extend far beyond Earth's own borders. We are, in a very real sense, children of Jupiter, not born from it directly, but made possible by the specific conditions its existence created. This realization connects to one of the deepest questions in modern astronomy. How common are systems like ours? The Kepler Space Telescope, launched in 2009 and operational until 2018, discovered thousands of exoplanets orbiting other stars. The diversity of planetary systems it revealed was astonishing. Many systems have hot Jupiters, gas giants orbiting within a few million kilometers of their host stars, worlds that completed their inward migration without a Saturn to pull them back, worlds that would have obliterated any inner rocky planets in their path. Others have super-Earths, planets with masses between Earth and Neptune, packed closely together in tight orbits. Some systems have planets in resonant chains, their orbital periods locked in mathematical ratios. Others have planets on wildly eccentric orbits, careening from near their stars to the frigid outer reaches and back again. Each system is a different outcome, a different roll of the same cosmic dice, governed by the same laws of physics, but shaped by different initial conditions and different accidents of history. Our solar system, with its clear separation between inner rocky planets and outer gas giants, its relatively circular orbits, and its Jupiter at a comfortable 5.2 astronomical units, appears somewhat unusual among the systems discovered so far. This does not mean it is unique. Our detection methods are biased toward finding certain kinds of planets, large ones orbiting close to their stars, and we may be underestimating the prevalence of solar system analogues. But the available evidence suggests that the specific architecture of our solar system, shaped so profoundly by Jupiter, is not the most common arrangement. It may not be rare, but it is not typical. The TESS mission, launched in 2018 as a successor to Kepler, has continued to expand the census of exoplanets, focusing on nearby bright stars where follow-up observations are easier. TESS has confirmed hundreds of new planets and candidates, further enriching the diversity of known planetary architectures. Ground-based radial velocity surveys have found cold Jupiters, gas giants at distances comparable to our Jupiter's orbit, around perhaps 10 to 15% of Sun-like stars. This is a significant fraction, but it means that the majority of Sun-like stars do not have a Jupiter analogue, and among those that do, the orbital parameters, eccentricities, inclinations, and companions vary widely. No two Jupiter-like planets are identical. Each one exists in a unique configuration, shaped by its own formation history, its own disk conditions, its own gravitational interactions with neighbors. The implications are staggering. If only 10 to 15% of Sun-like stars have a Jupiter analogue, and if the specific properties of that Jupiter matter for the habitability of inner rocky planets, then the subset of planetary systems capable of supporting complex life may be smaller than we assumed. Not zero, not negligible, but smaller. The question becomes, how sensitive is the outcome to the details? Does the inner solar system care whether Jupiter is at 5 astronomical units or 6? Does it matter whether Jupiter's eccentricity is 0.05 or 0.1? Does the presence or absence of a Saturn-like companion change everything or nothing? These are quantitative questions, and they require quantitative answers that we are only beginning to develop. If our solar system's architecture is partially a consequence of Jupiter's particular history, and if that history involves a chain of events that could easily have gone differently, then the conditions for complex life may be more finely tuned than we often suppose. Not impossibly rare, but not inevitable either, somewhere in between, contingent, dependent on the right planet, in the right orbit, with the right migration history, and the right set of gravitational interactions with its neighbors. Consider what this contingency means in concrete terms. The Milky Way contains roughly 200 to 400 billion stars. Current estimates suggest that most of these stars have at least one planet, meaning there are likely more planets than stars in our galaxy. Among these hundreds of billions of planetary systems, some fraction will have gas giants. Some fraction of those gas giants will be in orbits similar to Jupiter's, not too close, not too far, with low eccentricity and moderate inclination. Some fraction of those systems will also have rocky planets in the habitable zone, the region around a star where liquid water can exist on a planet's surface. But even among those systems that check all these boxes, the specific migration history of the gas giant matters. A Jupiter that migrated too far inward would have destroyed the rocky planets. A Jupiter that never migrated at all might not have delivered enough water to the habitable zone. The window of acceptable outcomes may be narrow. We do not yet know how narrow that window is. That is the honest answer. We do not have enough data. We have one solar system to study from the inside, and thousands of exoplanetary systems observed from afar, most of them incompletely characterized. The statistics are improving with every new survey, every new telescope, every new discovery. But the question of how common life-bearing planets are, and how important a Jupiter-like planet is to that outcome remains one of the great open questions of the 21st century. The observational challenge is formidable. Detecting a Jupiter analogue, a gas giant in a wide orbit with low eccentricity, requires either decades of radial velocity monitoring or a fortunate geometric alignment for a transit observation. Most exoplanet detection methods are biased toward finding planets that are close to their host stars because the signals are stronger, more frequent, and easier to confirm. A planet like our Jupiter, orbiting at 5 astronomical units with a 12-year period, would produce a radial velocity signal of roughly 12 meters per second, detectable but requiring long baselines and high-precision instruments. The transit probability for a planet at Jupiter's distance is roughly 1 in 1,000, meaning that out of 1,000 stars with Jupiter analogues, only one would show a transit from our vantage point. These detection biases mean that the census of cold Jupiters is far less complete than the census of hot Jupiters and close-in super-Earths. We are looking at the exoplanet population through a keyhole, and the view is skewed toward worlds that look nothing like the planets in our own system. The rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee in their 2000 book, argues precisely this point. Complex multicellular life, the kind that builds civilizations and writes books and launches spacecraft, may require a confluence of factors so specific and so improbable that it is genuinely rare in the universe. A Jupiter-like guardian, a large stabilizing moon, plate tectonics, a magnetic field, the right amount of water, the right amount of carbon, the right distance from the right kind of star. Each factor narrows the probability, and Jupiter is one of the most important factors on the list. This is not science fiction. This is the current state of our understanding. We live in a solar system shaped by contingency. We exist because Jupiter took a particular path through the history of our planetary system, and we understand that path only partially through the indirect evidence of gravity measurements, atmospheric spectroscopy, and computer simulations. We are relying on an ingredient we do not fully understand, citing it as essential to a process we cannot yet explain. In a universe where our sample size is exactly 1, the humility required here is immense, and the questions it raises are some of the most profound in all of science. What does it mean to live in a solar system shaped by a planet we barely understand? This is not a rhetorical question. It has both practical and philosophical dimensions, and both deserve careful consideration. On the practical side, our ability to identify potentially habitable exoplanets, worlds beyond our solar system where life might exist, depends critically on our understanding of how planetary systems form and evolve. If Jupiter's migration reshaped our inner solar system, clearing space for Earth and delivering water to our world, then the presence or absence of a Jupiter-like planet in an exoplanetary system is a critical variable in assessing that system's potential for habitability. But we do not yet have a reliable model for predicting whether a given star will produce a Jupiter-like planet in a Jupiter-like orbit. The formation of gas giants depends on the mass of the protoplanetary disk, the distribution of solid material, the timing of core accretion, the lifetime of the gas disk, and the gravitational interactions between multiple forming planets. All of these factors vary from star to star, from disk to disk, from system to system. We are extrapolating from a sample of 1, our own solar system, and we cannot be sure our extrapolations are correct. The James Webb Space Telescope, launched in December of 2021, is beginning to characterize the atmospheres of exoplanets, detecting molecules like water vapor, carbon dioxide, and methane in the atmospheres of gas giants, and even some smaller worlds. Future missions will push this capability further, potentially detecting biosignature gases, molecules that might indicate the presence of life in the atmospheres of Earth-sized planets in the habitable zones of nearby stars. But interpreting these detections will require context. A detection of oxygen in an exoplanet's atmosphere could indicate photosynthetic life, or it could indicate abiotic processes, geological or photochemical reactions that produce oxygen without biology. Distinguishing between these possibilities will require understanding the full planetary system, including whether a Jupiter-like planet exists, what its mass and orbit are, and how it might influence the formation an evolution of the potentially habitable world. Jupiter, in other words, is not just a subject of study. It is a necessary piece of the puzzle for understanding habitability throughout the galaxy, and we are still missing pieces of Jupiter itself. On the philosophical side, Jupiter's story challenges some of our deepest assumptions about order and stability in the cosmos. We are accustomed to thinking of the solar system as a clockwork mechanism, stable and predictable, the planets tracing their eternal ellipses around the sun. The laws of gravity are well known, the orbits are precisely measured, the future is, in principle, calculable for millions of years ahead. But this apparent clockwork stability is the end state of a turbulent history. The solar system we see today is the survivor of a chaotic adolescence, a period of giant impacts, orbital migrations, and gravitational scattering that could have produced any number of different outcomes. The order we observe is not inevitable, it is contingent, and it was shaped in large measure by Jupiter. There is a paradox buried in this realization. We use the tools of science, tools of order and logic and mathematics, to study a history that was fundamentally chaotic. We seek laws and patterns in a system that reached its current configuration through a sequence of contingent events, any one of which could have gone differently. The laws of physics are deterministic. Given the exact initial conditions of the solar nebula, the exact positions and velocities of every particle, the outcome would be uniquely determined. But we do not know the initial conditions. We cannot know them. They are lost to the past, erased by 4.5 billion years of subsequent evolution. So we simulate. We run thousands of variations, tweaking the mass of the disk, the position of the snowline, the timing of Jupiter's gas accretion, and we watch what happens. Each simulation produces a different solar system. Some look like ours, most do not. The range of possible outcomes is vast, and we are left with the humbling recognition that our solar system is one possibility among many, not the inevitable product of physical law, but a specific, contingent outcome of specific, contingent initial conditions. There is a deeper lesson here about the nature of scientific knowledge. We build models, we test them against observations, we refine them, and then we discover something unexpected, a dilute core, a deep weather layer, a set of polar cyclones arranged in pentagons and octagons, and we realize that our models were incomplete. Not wrong, necessarily, but insufficient. The universe is always more complex than our representations of it. Jupiter is a particularly vivid reminder of this truth, because it is the most massive, most visible, most studied planet in our solar system, and it is still full of surprises. Consider what it would mean if we could fully understand Jupiter. If we could map its interior precisely, model its dynamo completely, explain every storm and every wind, and reconstruct its formation history from the first planetesimal to the present day. That understanding would not just be about one planet. It would be a Rosetta Stone for planetary science, a key that unlocks the formation and evolution of giant planets everywhere in the universe. It would constrain models of protoplanetary disk evolution, giant impact dynamics, planetary migration, and atmospheric circulation. It would sharpen our predictions about the kinds of planetary systems that can produce habitable worlds. It would, in a very real sense, tell us something about the probability of our own existence. The James Webb Space Telescope has already begun to transform this picture from the observational side. Since becoming operational in 2022, JWST has observed the atmospheres of dozens of exoplanets in unprecedented detail, using its infrared instruments to detect the chemical fingerprints of water vapor, carbon dioxide, methane, and sulfur dioxide in the skies of worlds orbiting distant stars. Some of these worlds are gas giants, comparable to Jupiter in mass and composition. Others are smaller, stranger, occupying categories with no analogue in our solar system. The data from JWST is building a comparative framework that allows us to place Jupiter in the broader context of planetary diversity. When we measure water abundance on a hot Jupiter orbiting a star 40 light-years away, the benchmark against which we compare is our own Jupiter. When we model the atmospheric circulation of a brown dwarf with banded cloud patterns, the theory we test was developed to explain the bands on Jupiter. Our solar system's giant planet is the calibration point for the entire field of exoplanet atmospheric science. Understanding Jupiter better means understanding every giant planet better. and that understanding cascades through the field, improving our models of habitability, atmospheric evolution, and planetary formation. We are not there yet, not even close, but every orbit Juno completes, every data point the microwave radiometer records, every gravity harmonic refined to another decimal place, brings us incrementally closer. Science is patient work. It moves in small steps, not in cinematic leaps, and the small steps, accumulated over decades and centuries, eventually cover enormous ground. There is something worth noting about the way Jupiter has been studied over the centuries, because it mirrors the way science itself evolves. Galileo saw moons. 2 centuries later, astronomers measured the Great Red Spot. A century after that, we sent our first probes. Each era of observation was limited by the instruments available, and each era's scientists believed they understood Jupiter reasonably well. Galileo could not have imagined metallic hydrogen. Pioneers' engineers did not anticipate the dilute core. The scientists who designed the Galileo probe could not have predicted the depth of the weather layer. At every stage, Jupiter has been stranger than the previous generation believed. And there is no reason to think our generation is the exception. There is no reason to think that the Juno results represent the final word. They are the latest word. The next word will come from the next mission, or from a theoretical breakthrough that reinterprets the existing data, or from an observation of an exoplanet that illuminates a process we never considered. There is a specific kind of courage in this patient work. The courage to ask questions whose answers may not come in your lifetime. The courage to build instruments that may return data you will never see analyzed. The courage to invest decades of effort in understanding a planet that stubbornly refuses to be understood. The scientists who designed Juno began their work in the late 1990s. The spacecraft was not launched until 2011. It did not arrive at Jupiter until 2016. The data analysis will continue for years beyond the end of the mission. The full implications of the results may not be clear for another generation. Consider the specific career trajectories involved. A graduate student who worked on the Juno proposal in the late 1990s would now be a senior professor, perhaps approaching retirement, still publishing papers from a mission that has been part of their professional life for over a quarter century. Their students, and perhaps their students' students, will inherit the dataset and continue to mine it for insights. The investment of human effort across these timescales is itself a remarkable phenomenon, a testament to the institutional structures of science that allow knowledge to accumulate across generations, each building on the work of predecessors, each adding layers to a picture that no single individual could complete alone. This is the time scale of understanding, not months, not years, generations, and it mirrors in its own way the timescale of Jupiter itself. A planet that has been evolving for 4.5 billion years does not yield its secrets in a decade. It requires patience commensurate with its age, effort commensurate with its scale, and humility commensurate with its mysteries. Jupiter hangs in the night sky, a steady point of golden light, brighter than any star except the most brilliant. It has been there, in one form or another, since before our planet had continents, since before the first microbe stirred in the primordial ocean, since before life of any kind existed anywhere in the solar system. If indeed it exists anywhere other than Earth, it will be there long after our civilization has run its course, still spinning, still churning, still hiding its secrets beneath those beautiful, terrible clouds. The storms will come and go. The magnetic field will drift and reconfigure. The metallic hydrogen will flow in patterns we have never observed and may never observe. And the dilute core, whatever its origin, will continue its slow evolution in the crushing darkness at the heart of the planet, a mystery wrapped in liquid metal, wrapped in cloud. Every time we look at Jupiter, we are looking at our own past. The history of the solar system is written in that planet's interior. The conditions that allowed Earth to form, to acquire water, to develop an atmosphere, to sustain life, all of these were shaped by what Jupiter did in its first few million years. We are looking at the architect of our world, and the architect's blueprints are still being deciphered. Jupiter is not what you think. It is not a simple gas giant, passively orbiting the sun in the outer darkness. It is not a failed star that fell short of ignition. It is not a well-understood body whose story has been told, whose mysteries have been catalogued and filed away. It is not the reassuring giant that protects us from comets, a benevolent guardian keeping watch over the fragile inner worlds. It is none of these things, and it is all of them, and it is more. Jupiter is a world of liquid metal and crushing pressure, a world where hydrogen, the simplest element, is transformed by sheer force into something alien, something that conducts electricity and generates magnetic fields that reach across hundreds of millions of kilometers of empty space. A world with no surface, no ground, no place to stand, just an endless gradient of thickening gas becoming hot, liquid becoming denser, liquid becoming metallic, ocean becoming, at the very center, a shattered and smeared remnant of the rocky seed from which it grew. Jupiter is a world of storms that dwarf planets, cyclones arranged in geometric patterns at the poles, each one the size of a continent. A great red spot that has endured for centuries but is now shrinking, its future uncertain, its mechanics still unexplained. Jet streams that howl at hundreds of kilometers per hour, extending 3,000 kilometers down into the planet, powered not by sunlight, but by the slow release of heat from the planet's birth. The weather on Jupiter is not decoration. It is the visible expression of processes rooted deep in the planet's interior, processes that connect the cloud tops to the metallic hydrogen layer in a single, continuous, turbulent engine. Jupiter is a world that moved, that migrated through the inner solar system billions of years ago, scattering planetesimals, truncating Mars, reshaping the asteroid belt, and then reversing course, pulled back outward by the gravitational choreography with Saturn. If this happened, and the evidence suggests it did, then the inner solar system we know is a product of that migration. Earth exists because Jupiter left. Mars is small because Jupiter visited. The asteroid belt is sparse and mixed because Jupiter stirred it. We know less than we think. That is perhaps the most important lesson Jupiter has to teach us. We build models, and the models work for a time, until new data arrives and the models break. We launch probes, and the probes return data that contradicts our expectations. We refine our theories, and the refined theories raise questions that are harder and deeper than the ones we started with. This is not failure. This is science working as it should. The universe is not obligated to be simple. It is not obligated to match our intuitions. And Jupiter, more than any other body in our solar system, has demonstrated this truth over and over again. There is a loneliness in the realization that our existence may be contingent on the specific behavior of a gas giant 500 million kilometers away. Not the loneliness of cosmic distance, though that is real enough, but the loneliness of specificity. We are here because Jupiter followed a particular path, a different migration, a different mass, a different formation history, and the solar system might have produced a different set of planets, a different Earth, or no Earth at all. We are the outcome of one particular roll of the cosmic dice, and the dice were weighted by Jupiter. But there is also wonder, because the same contingency that makes our existence fragile also makes it precious. If we are here because of a specific chain of events stretching back 4.5 billion years, then every moment of consciousness, every question asked, every telescope pointed at the sky, is the continuation of that chain. We are the universe looking at itself through eyes that exist, because a gas giant wandered through the inner solar system and then wandered back. We are the universe asking questions about its own architecture, using instruments built from the same atoms that were once scattered by Jupiter's gravity. And what questions they are! Not small questions, not questions about comfort or convenience, but questions about the nature of reality itself. Why is there something rather than nothing? Why does matter organize itself into stars and planets, and, on at least one small world, into beings that can contemplate their own origins? Jupiter does not answer these questions. No planet can, but Jupiter sharpens them. It forces us to confront the specificity of our situation, the narrowness of the path that led to us, and the vast, silent expanse of possibilities that did not lead anywhere at all. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. And in that brief window of understanding, we have chosen to look outward, to study the planets and the stars, to ask how we got here and whether we are alone. Jupiter is central to that inquiry. It always has been. From Galileo's first telescopic observation to Juno's latest gravity measurement, Jupiter has been asking us to look more carefully, to think more deeply, and to accept that the universe is stranger than we imagined. The Juno spacecraft orbits Jupiter still. Every 53 days, it swoops in close, measuring, sampling, photographing. The data flows back to Earth at the speed of light, arriving 43 minutes later at the Deep Space Network antennas in Goldstone, Canberra, and Madrid. Scientists study the data, run simulations, publish papers, debate interpretations. The slow work of understanding continues. And with each orbit, each measurement, each paper, the picture of Jupiter grows a little more detailed. Not clearer necessarily, sometimes more confusing, but richer, deeper, more honest. Think about what that process represents. A species that has existed for roughly 300,000 years, a blink in Jupiter's timescale, has built machines capable of traveling 500 million kilometers, surviving radiation that would kill any living thing, and returning data precise enough to map the distribution of mass inside a planet. We cannot visit Jupiter ourselves. We cannot touch its clouds, or swim its metallic ocean, or stand at its core, but we can send our instruments, our equations, our questions. And the planet answers, in its own language, in the grammar of gravity and electromagnetism and fluid dynamics. And we translate imperfectly, gradually, with increasing sophistication, but never with finality. The Europa Clipper is on its way. JUICE is on its way. Future missions not yet designed will follow. Perhaps one day, decades or centuries from now, we will send a probe deep enough into Jupiter to touch the metallic hydrogen layer, though the engineering challenges are beyond anything we can currently envision. Perhaps we will develop new materials that can withstand pressures of millions of atmospheres and temperatures of tens of thousands of degrees. Perhaps we will find a way to transmit data from depths where radio signals cannot penetrate, using some technology we have not yet invented. Perhaps we will map the dilute core in 3 dimensions, resolving the question of whether it was primordially mixed or shattered by impact. Perhaps we will understand the polar cyclones, the deep weather, the magnetic field anomalies, perhaps. But perhaps is enough. Perhaps is what science runs on. Not certainty, not finality, but the steady, patient pursuit of understanding in the face of irreducible complexity. Jupiter is complex. It has always been complex, and it will remain complex long after we have exhausted our current tools and models. The gas giant does not care about our theories. It simply is what it is, turning in the dark, radiating its ancient heat, surrounded by its retinue of moons, wrapped in storms and clouds and liquid metal and mystery. The next time you are outside on a clear night, look for the brightest point of golden light in the sky. Not twinkling, because planets do not twinkle. Steady and calm, like a lamp in a distant window. That is Jupiter. That is the planet that shaped your world. The planet that may have made your existence possible. The planet that, after 400 years of observation and 9 spacecraft encounters and thousands of scientific papers, remains fundamentally surprising. It is not what you think. It never was. And that, perhaps, is the most Jovian truth of all. The universe does not owe us comprehension. It only offers us the chance to look, to measure, to wonder, and to sit in honest awe before the things we cannot yet explain. The clouds turn, the storms churn, the metallic ocean flows in darkness, and Jupiter keeps its secrets patient and immense, waiting for better questions.